Hello viewers, welcome to APCC LMS portal. Myself, M. Pradeep, lecturer in biotechnology, and today we are going to discussing about isotopes. Before going to the topic, first we briefly discussing about atom and its structure. Atom. What is an atom? Atom is the basic unit for any matter or substance present in the universe, and atom contain center nucleus and surrounding to the nucleus orbits present, and orbits contain orbitals. Within the orbitals, electrons present. Nucleus contain protons and neutrons, collectively called as nucleons. The sum of protons and neutrons is called as mass number. Here A equal to Z plus N. A equal to mass number, Z equal to proton number, and N equal to neutron number. So mass number is the sum of protons and neutrons present in the atomic nucleus, and the number of protons present in the nucleus is known as atomic number. It can be calculated by using the formula Z equal to A minus N. Here Z equal to atomic number, A equal to mass number, and N equal to neutron number. Then isotopes. What are isotopes? Isotopes are the atoms with the same number of protons but different in neutron number. So isotopes of the atoms are isoforms of same atom, but they contain same atomic number but neutron number is different. Or in other words, atoms of the same element with different mass numbers. That means Z is same for all atoms, but mass number and neutron numbers are different. For example, if we take hydrogen isotopes, this is H11, one atomic number and mass number is also 1. This is not protium. This is 1H2. This is deuterium. 1H3. This is tritium. All these are hydrogen isotopes. Here the mass number is 1. Here the mass number is 2. Here the mass number is 3. So atoms of the same element, same atoms but have different mass numbers. So these are isotopes. Similarly, carbon isotopes. In here also, all these are carbon atoms with same atomic number but mass number are different. As mass number is different, neutron number is also different. So isotopes are the atoms of same element with different mass number or neutron numbers. Determine the number of neutrons in each isotope. The formula is N equal to A minus Z. N equal to neutron number. We can calculate neutron number by using this formula. N equal to A minus Z. As isotopes contain different neutron but atoms of the same atoms. So they contain different neutron number. How can we calculate the atomic number? Neutron number means N equal to A minus Z. That means mass number minus atomic number. If we take uranium 92-238, this is a uranium isotope. Its atomic number is 92 and mass number is 238. If we calculate the neutron number, mass number 238 minus 92, it gives 146 neutron. That means uranium 92-238 contain 146 neutrons. Similarly, krypton 3684. Krypton, the atomic number is 36 and mass number is 84. If you want to calculate the neutron number, 84 minus 36, that gives 48 neutron. That means krypton contain 48 neutrons. Similarly, chlorine 1735. 17 is the atomic number, 35 is the mass number. The difference between mass number and atomic number gives neutron number, that is 18 neutrons. Similarly, carbon 612. This is another isotope of carbon. Its atomic number is 6 and mass number is 12 and the number of neutrons present is 12 minus 6, that is equal to 6 neutron. So these are the different isotopes, and each isotope has different neutron numbers, and a neutron number can be calculated by using n equal to a minus z formula. Notation of isotope. How can we represent isotopes? There are two main representations generally used for isotopes. First one is, if you take X as an atom, in downwards, that is Z. Z is called atomic number, and top there is mass number A, that is mass number. This is one way of representing the isotopes. For example, the different carbon isotopes can be represented as like this. That means all carbon contain same atomic number, but mass numbers are different. This is one way of representing isotopes. The another way of representing isotopes is this. Here X equal to element or atom and A equal to mass number. Example. There are different carbon isotopes can be represented in another way. C12, and that means carbon mass number is 12. C13, carbon mass number is 13, and C14, carbon mass number is 14. In this way, we can represent isotopes using any of the notation. First, carbon isotopes. Carbon has 15 known isotopes from C8 to C12. That means mass number 8 to mass number 22. There are 15 known isotopes for the carbon exist. Among the carbon isotopes, C12 and C13 are stable. Stable means they doesn't possess any radioactivity. So among the carbon isotopes, C12 and C13 are stable isotopes and doesn't show any radioactivity. The longest lived radioactive isotope is C14. C14 is not a stable isotope. It has longest life and exhibit radioactivity, and the half-life of this C14 radioactivity is 5730 years. These are three natural isotopes. C12, C13 and C14 are the three common natural isotopes present in the nature. Among these three natural isotopes, C12 and C13 are stable isotopes and C14 is unstable isotope. That means it exhibits radioactivity and its half-life is 5730 years. That means the initial concentration degraded into half of its original amount takes 5730 years. That is T half. So C14 is the only natural isotope, carbon isotope that exhibits radioactivity. C14 is the only carbon radioisotope found in nature and formed cosmogenic. How C14 isotope formed means cosmogenically it formed like this: N14 nitrogen plus neutron. By the addition of one neutron to the N14, it gives carbon 14 isotopes and release one proton. This is the way of carbon 14 formed naturally by cosmogenic action. The most stable artificial radioisotopes are C11, which has a half-life of 20.364 minutes. Whatever we have studied so far, that is C12, C13 and C14 are natural isotopes for the carbon. Among the natural isotopes, C12 and C13 are stable isotopes and C14 exhibits radioactivity with highest half-life of 5730 years, and C14 formed cosmogenically by colliding nitrogen with neutron and gives C14 and proton use. Remaining all isotopes are called artificial carbon isotopes, and all these are radioactive isotopes. Among the synthetic or artificial carbon isotopes, C11 is the possess highest half-life of 20.364 minutes. All other radioisotopes have half-life under 20 seconds. Remaining all artificial isotopes have half-life very less amount of time, that is 20 seconds. The least stable isotope, that is artificial isotope, is C8 with half-life of 2.0 into 10 to the power of minus 21 seconds. This is the least half-life containing isotope, that is C8. Here if you take, there are 4 carbon isotopes here showing. Among the 4 carbon isotopes, C12, C13 and C14 are natural isotopes and C11 is synthetic isotope. C12, C13 are stable isotopes and C14 is natural isotope but it exhibits radioactivity. C11 is synthetic isotope and it exhibits radioactivity. It releases beta particle, that means positron, whereas C14, which is a natural isotope but exhibit radioactivity, is a beta decay radioactive element. Next, hydrogen isotopes. Hydrogen naturally has 3 isotopes. Those are 1H1, that means protium, 1H2, that is deuterium, 1H3, that is tritium. These 3 are natural hydrogen isotopes. There are other synthetic isotopes also for hydrogen, but these are natural isotopes for hydrogen. Hydrogen has 3 naturally occurring isotopes as shown above. The first 2 of these are stable isotopes. That means protium and deuterium are stable isotopes. That means they doesn't possess any radioactivity. Whereas tritium, that is 1H3, has half-life of 12.32 years. That means tritium exhibits radioactivity. Other are more heavier isotopes which are all synthetic. Other than these 3, remaining all are heavier isotopes. That means they have more mass number than 3 and all they are synthetic and have half-life less than giptosecond. That means 10 to the power of minus 21 seconds. Less than minus 10 to the power of minus 21 seconds. Their half-life is that. Of these, H5 is the most stable and H7 is the least stable isotopes. So these are the different hydrogen isotopes. Next, types of isotopes. Based on the exhibition of showing or exhibiting radioactivity or not, the isotopes are categorized into 2 types. Those are stable isotopes and unstable isotopes. If any isotope doesn't exhibit radioactivity, then they are called stable isotopes. So stable isotopes are those isotopes which doesn't possess any radioactivity. Some isotopes exhibits radioactivity and those isotopes that are exhibiting radioactivity are called unstable isotopes. So in this way, based on the property of radioactivity, whether they are exhibiting or not, the isotopes are categorized into stable isotopes and unstable isotopes. Stable isotopes doesn't show any radioactivity, whereas unstable isotopes exhibits radioactivity. Stable isotopes, as I said earlier, they not undergo any radioactivity or nuclear decay. So they are non-radioactive form of isotopes. The unique properties of stable isotopes enable them to be used in broad variety of applications. That is, water and soil management, we can use stable isotopes, and environmental studies also we can use stable isotopes. Nutritional assessment studies also stable isotopes are useful, and in forensic studies also stable isotopes are useful. For example, deuterium, that is 1H2, isotope of hydrogen, twice the heavy of normal general hydrogen, is predominantly used in nutritional research, whereas nitrogen 15 is the isotope of nitrogen, is the most common stable isotope used in agriculture. These are the various applications of stable isotopes. Another one is unstable isotopes. Unstable isotopes undergo radioactivity or nuclear decay. So they are called radioisotopes. So unstable isotopes are also known as radioisotopes. isotopes. In unstable isotopes, nucleus is unstable because they contain unequal number of protons and neutrons. So they contain the nucleus of unstable isotopes is very unstable and dissipate excess energy or excess nucleons in the form of alpha rays, alpha particles or beta particle or gamma rays, either in the form of particles or in the form of electromagnetic radiation. They exhibit excess energy, dissipate excess energy. Hydrogen is the lightest element. It contains three isotopes, that is H1, H2, H3. H1 and H2 are stable isotopes as I said earlier, but H3 is tritium, is radio isotope and exhibits radioactivity. Similarly, cobalt-60 is extensively employed as a radiation source to arrest the development of cancer. So, in order to arrest the cancer cell to divide, cobalt-60 used to emit radiation, and that emitted radiation used for killing the cancer cells. In this way, unstable isotopes have several applications in medicine and also agriculture also. So, we'll know more about those things in another classes. But unstable isotopes is cobalt-60 and tritium are unstable isotopes and exhibits radioactivity. Next, atomic mass and atomic weight. Before going to the atomic mass and atomic weight, first we know the atom. Atom is the basic unit of any matter or substance. This is atom. This is center nucleus and this surrounding orbital. This is atom. Atom is the basic unit for any matter or substance. Then element. What is element? It is group of similar atoms. So complex of similar atoms. So element made up with two or more similar atoms. Here you see these are element that contain three similar atoms. So this is element. Element made up with two or more similar atoms. Next, molecule is a complex of two or more dissimilar atoms. Here you see this is one type of atom, this is another type of atom, and this is another type of atom. This is a molecule because it contains different types of atoms. So it is molecule. Then atomic mass. What is atomic mass? Atomic mass always calculated to an atom. So atomic mass always calculated to an atom. What is atomic mass? Atomic mass is the sum of protons and neutrons present in the nucleus of that atom. And atomic mass units are daltons. The units for atomic mass is daltons. If you take example, carbon 612. That means carbon atomic number is 6 and mass number is 12. That means it has 6 protons and 6 neutrons. So mass number is 12. If you take carbon, carbon contains in its nucleus 6 protons and 6 neutrons. So the atomic mass is 12. So atomic mass is always the sum of protons and neutrons present in the nucleus of an atom. So atomic mass always calculated to an atom. And the units for atomic mass is daltons. Whereas atomic weight, an element may contain different isotopes of same atom in different proportions. So atomic weight always calculated to an element. Element is, what is element? Element is the group of similar atom or complex of similar atom. That means element contain similar atoms. For example, nitrogen N2, it is an element. Nitrogen element contain two nitrogen isotopes. For example, N14 and N15. So elements may contain same isotopes or dissimilar isotopes. For example, N2 element contain both N14 and N14 or may also sometimes may also contain N14 and N15, and their proportions also different. So atomic weight is calculated based on isotopes composition. So for example, if we take N2 element, we take N2 contain two nitrogen isotopes. Those are N14 and N15, and their proportions are 65% and 35%. That means N2 element contain N14 in 65% and N15 element in 35%. Then atomic mass of N14 is, generally we calculate atomic mass, that is a proton and neutron number, and so N14 atomic mass is 14. That is mass number is equal to atomic mass, and N15 contain mass number is 15. That is 15 daltons. Then atomic weight of nitrogen element can be calculated as follows. If you want to calculate the nitrogen atomic weight, nitrogen element atomic weight, atomic mass of N14 into percentage of N14 in that element by 100 plus atomic mass of N15 isotope into percentage of N15 isotope in that element by 100. As I said earlier, 14 is the atomic mass of N14 nitrogen and the percentage of N14 nitrogen in that element is 65% by 100 plus 15 is the atomic mass of N15 isotope and the proportion is 35% by 100. So 14 into 0.65 plus 15 into 0.35 that equal 9.1 plus 5.25. So the atomic weight of nitrogen element in this case is 14.35 atomic mass units. So the atomic weight, the units for atomic weight is atomic mass units. So this way atomic mass always calculated to an atom, whereas atomic weight always calculated to an element. Element may contain different isotopes in different proportions. So in order to calculate the atomic weight, we need to consider the different isotopes and their proportions also to calculate the atomic weight. And the units for atomic weight is atomic mass units. Differences between atomic mass and atomic weight. This is atomic mass. This is atomic weight. Atomic mass is the sum of protons and neutrons of an atomic nucleus. That means protons and neutrons collectively gives atomic mass, whereas atomic weight is the sum of products of masses and their proportions of different isotopes exist in an element. So atomic weight is the sum of products of protons, mass and proportions of isotopes exist in an atomic and element is atomic weight. And atomic mass is related to single atom, whereas atomic weight is related to an element. So always atomic weight calculated to element, whereas atomic mass calculated to single atom. And atomic mass is always whole number. It give 2, 4, 6 like that, always whole number. Whereas atomic weight is may or may not whole number. That means it sometimes give fractions also. So this is atomic weight. Atomic mass is always whole number, whereas atomic weight is may or may not whole number. And the units for atomic mass is daltons, whereas the units for atomic weight is atomic mass units. Then how can we calculate the atomic mass and atomic weight? They can be calculated by using mass spectroscopy. Atomic mass spectroscopy or atomic mass spectrophotometer can be used for the study of atomic mass or atomic weight of any molecule or substance. This is all about isotopes and their properties.